Acetic acid production from rhodium catalyzed carbonylation of methanol, a project by Peter Arnadoff, Daniela Peña-Castro, Ethan Plummer, Elizabeth Sarando, and Haley Williams. This presentation will give you a broad overview of the chemical process we investigated for the production of acetic acid from carbon monoxide and methanol. We'll discuss our design specifications and assumptions, our safety considerations, and our process for determining our results. We will then interpret our results and draw our conclusions. Acetic acid is produced on a large scale for use as a raw material in the manufacture of many organic products. By the 1960s, rhodium and iodine catalysts were beginning to replace the old methods of production which involved the use of acidic catalysts. This development led to reductions in capital and operations costs. The production of acetic acid by way of carbon monoxide and methanol is a well-characterized exothermic reaction. According to a 1975 article in Industrial Engineering Chemistry Product Research by Jensen and others, the standard heat of reaction is about -33 kilocalories per mole. There is an undesired reaction we must take into account, namely the reaction between carbon monoxide and water, producing carbon dioxide and hydrogen gas. The standard heat of reaction of this undesired reaction was calculated using a relationship found in Perry's Chemical Engineer's Handbook.
As part of the design process, some specifications and assumptions had to be made. First, a homogeneous rhodium-catalyzed methanol carbonylation reaction was assumed. This was going to take place in an adiabatic packed reactor. For this reaction, the pressure range was going to be from 1 to 50 atm with an initial pressure of 1 atm. The temperature range was 150 to 225 degrees Celsius with an initial temperature of 150 degrees Celsius. The catalyst weight was set to 64 kilograms with an equimolar fit of an initial fit of 10 moles per second, and due to the high selectivity provided by the catalyst, even though there is an undesired reaction, its effects were going to be ignored for the design equation of this reaction. To simplify the design process, assumptions such as adiabatic operation, neglecting shaft work, neglecting enthalpy change due to mixing, and assumption of no phase change in the reactor were made. These assumptions, among others, will be further explained as we go through the algorithm. In terms of safety consideration, each of the safety data sheets of our components for the reaction were taken into account in order to know about the flammability, toxicity, and possible corrosive nature of the components that we were using. Based on the safety considerations previously presented, personal protective equipment must always be used when operating this reactor. Also, environmental safety must be taken into account by making sure that every chemical is disposed properly according to its SDS. Also, ensuring proper ventilation for the lab set in which this system will take place, and removing any source of ignition prior to initiating the experiment, as a couple of our components may be flammable.
To begin analyzing our process, we started with the first step of the algorithm outlined in our textbook. General mole balances were applied to each of the species. The change in the molar flow rate of each species with respect to the catalyst weight is equal to the rate of reaction of each species. The prime notation indicates that the reaction rates are based on the mass of catalyst. The next step was to define each rate law. The literature for our process confirmed that the rate was zeroth order. Therefore, the rate of reaction is simply dependent on the reaction rate constant, K. As mentioned previously, the high selectivity of our desired reaction allowed us to neglect the impact of the undesired reaction. Next, the stoichiometry expressions were explicitly defined. Since the reaction is taking place in the gas phase, the concentrations are a function of the pressure drop across the packed bed as well as the temperature change. Since epsilon is not equal to 0 in our case, the concentrations are also changing with volume. The change in pressure with respect to the catalyst weight is a function of the change in volume and the change in temperature. The pressure drop parameter, alpha, also greatly affects the change in pressure. This parameter was varied in our process code to observe what type of impact it would have on our system.
Continuing with the algorithm, we next consider energy balances. Our system is designed so that the reaction is carried out in an adiabatic packed bed reactor, for which case Q equals 0 and there's no heat flow into or out of our system. We're also neglecting shaft work. In the enthalpy analysis for this reaction system, we're neglecting any enthalpy changes that result from mixing. With this assumption, in the absence of a phase change and considering only constant heat capacities, the change in enthalpy can be expressed as delta H of a reaction for a specified temperature equals the standard enthalpy of reaction at a reference temperature, which we identified to be 25 degrees Celsius, plus the delta Cp term, which we identified to be 0 since we're considering only constant heat capacities. The enthalpy of reaction 1 is negative 33 kilocalories per mole, and the enthalpy of reaction 2 is approximately 10 kilocalories per mole. The standard enthalpy of reaction values are on the same order of magnitude for both reactions 1 and 2. This result further supports our assumption stated earlier that the undesired reaction can essentially be neglected in our analysis because the selectivity of our desired reaction is upwards of 99%. Combining the expressions in the previous slide and applying all stated assumptions, the following expression is the adiabatic energy balance for a tubular reactor, which relates temperature and conversion in a linear manner. Our adiabatic tubular reactor equation is then coupled with the differential mole balance expression written out in terms of the conversion of methanol and the desired reaction for acetic acid production. Combining all the steps of our algorithm, we now present this flowchart which details each stream. Initially, we consider an equal molar feed of carbon monoxide and methanol at 1 atm and 150 degrees Celsius with a pressure drop parameter alpha equal to 0.008 liters per kilogram. The optimum conversion for these operating conditions is 55% and results in an acetic acid production rate of 1,189 kilograms per hour, which is equivalent to 5.5 moles per second and requires 64 kilograms of catalyst to achieve. Furthermore, the outlet pressure is 0.52 atm and results in an exit temperature value of 750 degrees Celsius, signifying that this is a highly exothermic reaction.
When plotting conversion versus catalyst weight, we can see that as we move farther down the reactor with increasing catalyst weight, our conversion increased with an almost linear relationship.
Since the feed was equimolar, the concentration profiles of A and B overlap. The concentration of C reaches a maximum at around 64 kilograms of catalyst. The peak of the concentration of C, which is our product, helped us define the optimum operating conditions.
After modeling, we can see a linear relationship between conversion and temperature for our reaction.
The Levenspiel plot revealed something interesting. We chose to use a packed tubular reactor in our process, but we can see that the area under the curve, which represents the weight of catalyst needed, would be reduced if we were to use a fluidized CSTR instead. This would be something to keep in mind when actually designing a process.
Let's start altering our parameters with a lower bound alpha of 0.01. From this concentration versus catalyst weight plot, you can see that the concentration of our product has drastically increased. You can also see that the conversion is very high at about 86%. One caveat to this, however, is that we are using the entire length of our reactor at 100 kilograms of our catalyst is necessary. Now let's do an upper bound for alpha of 0.01. Comparatively, the concentration of our product did decrease. Additionally, the conversion decreased to about 55%. However, we did not need 100 kilograms of our catalyst. Instead, about half of that is needed. The optimal conversion is about half of what it was before at about 46%. Something that's important to note is that our exiting flow rates of our reactants is higher than the flow rate of our product. Now let's alter our initial pressure. Let's start with an initial pressure of 2 atm. As you can see, this graph looks very similar to the alpha value of 0.001. The concentration of our product is very high. Additionally, the conversion is very high as well at about 86% again. Note that we do still use 100 kilograms of the catalyst in order to achieve this. The exiting flow rate of our product is also very high. Now let's go ahead and increase the pressure to 50 atm to see what happens. It doesn't look like our system has changed very much. The biggest difference I see is that the p-value, p over p naught, is much higher than it was before. Lastly, let's alter the feed ratio of A to B, starting with doubling A. As expected, the concentration of A is much higher than it is of B, but it is also higher higher than the concentration of our product. The conversion is also very low and comparatively. We are not using all of the catalyst weight, which is great. However, our optimal conversion is only at 32%, which is not great. About twice as much A is leaving the reactor compared to our product. Now let's double the feed of B. As expected, the concentration of B is much higher than both A and C. It's interesting though that the conversion when doubling B is higher than the conversion when doubling A. The optimal conversion is at about 55%, which is better than it was before, but it's still not great. The exiting flow rate of B is still higher than the exiting flow rate of our product.
The following deductions can be drawn from our analysis on the effects of operating conditions. Bringing all these points together, we concluded that if a high conversion is desired, the feed pressure should be increased. As a result of increasing the pressure, more catalyst will be necessary, and the exit temperature will be relatively high.